talking about the periodic table of the elements in chemistry. Another little periodic table ditty that I thought was kind of cute. It's titled Disney's Character Chemistry. And it goes on to say, across the pond in the United Kingdom, science writer Kit Chapman has assembled a periodic table filled with characters from Disney movies. Chapman, who is both a Disney fanatic and a periodic table expert, tells CNE News it only took him a weekend to put the collection together. Chapman is author of the book Super Heavy, a book about the discovery of the elements beyond Lawrencium. In the Disney periodic table, the element iron, for example, is represented by Captain Hook from the film Peter Pan, because the villain has an iron hook for a hand. The element hafnium is represented by Ariel in The Little Mermaid, because hafnium is named after Copenhagen, where the fairy tale's author Hans Christian Andersen lived. And the element osmium, which derives its name from the Greek word for smell, this is kind of funny, is represented by Tarzan from the movie Tarzan, because Chapman explains, quote, let's be honest, there's no way Tarzan doesn't smell, unquote. Fans of the movie Finding Nemo won't find the characters Nemo and Dory on Chapman's periodic table. According to Chapman, they represent all the elements we haven't found yet, he quips. Explore Chapman's Disney periodic table at the net address Kit Chapman, that's kitchapman.co.uk/a-Disney-periodic-table. And always looking for some sort of ways to add a little bit of different outlook to scientific topics, and I thought this one was one that might appeal to the Disney fans out there. Anybody have any thoughts or questions? Okay, so first of all, this morning we'll wrap up our introduction to pharmacodynamics and pause ever so briefly and shift over to the autonomic nervous system, in which we'll take a look at some review topics with respect to autonomic anatomy, neurochemistry, and related generalized topics, leading our way into the discrete autonomic drugs, which will start with the parasympathetic side of things, and then move on as time allows into the sympathetic system. And in both cases, there are agonists and antagonists to talk about. So it's a rather diverse group of drugs that are involved with autonomic pharmacology. But I think a good place to start, it's kind of a traditional start. If you take a look at our textbooks or other textbooks on the subject, once the textbook has finished up with the introductory background topics like we've been covering here ourselves, then typically autonomics is the place that those books start. So you'll find reading early on in our in our books on autonomics, both general as well as parasympathetic and sympathetic topics. So let me set up our first PowerPoint here. So it's a good time to be thinking about whether there are any remaining questions and so on with respect to pharmacodynamics. And I'll get moved to a little bit later here in the PowerPoint, and then see, once we move through those issues, see if anybody has any concluding thoughts on pharmacodynamics before we enter into the autonomic realm. So there's our buddy Hipshot in this slide. If you take a look at his eyes, you can see that we've got a pretty wide open pupils there. We'll be paying attention to pupillary size. Picture of Bob is a little bit too small to tell, but we'll be taking a look at the cat Francis because he's sort of our autonomic hero. So let me move ourselves through these topics that we've been going through in the last few days. And if you recall from yesterday, we took a look at some cartoons of 7 transmembrane serpentine G-protein coupled receptors as tools in thinking about the architecture of G-protein coupled receptors and how that architecture ultimately contributes to the biochemical and pharmacological analysis of drug action that's occurring at G-protein coupled receptors, which is pretty common stuff because these receptors are so widely represented in nature. It's absolutely phenomenal how important these themes are, both in terms of the physiology of these receptors as well as their pharmacology. So we took a little bit of a look at Henry Bourne's, what I think is very nice cartoon of G-protein coupled receptors. And just a few more comments while we're looking at this cartoon. If you look at the outside portion of the receptor, there are, of course, some loops that are connecting the transmembrane segments. And there are binding determinants on those extracellular loops that allow participation of the very surface aspects of the receptor with ligands. But as we talked about yesterday, especially with respect to the first group of G-protein coupled receptors, the rhodopsin class of G-protein coupled receptors, which are typically interacting with small ligands such as neurotransmitters, the major binding determinants are found a little bit buried inside the membrane with respect to transmembrane segments, but there are some aspects of binding that occur with respect to the extracellular loops themselves, although those extracellular loops are more involved in sort of guiding ligand into the binding pocket than anything else. But when you think about the secretin class or the class B G-protein coupled receptors, which are typically somewhat larger ligands like peptides and larger hormones, as opposed to the small groups, which are characteristic of binding with the rhodopsin class. In the secretin class, since most of the larger molecule can't actually gain access to the inside of the receptor, the extracellular loops are more important in binding phenomena there than they are in the case of the smaller ligands. Now, on the other side of the membrane lie the so-called intracellular loops, And you can see those portrayed sort of center, but the lower part of the slide. And those loops are numbered um, according to what particular transmembrane segments are being linked together by the loop. So you've got intracellular loops 1, 2, 3, and sometimes 4. As we talked about yesterday, the cytoplasmic side of the receptor, or the inside of the receptor, is the home for the C terminus of the polypeptide receptor itself. And that pictured in this particular cartoon, the C terminus is free, but sometimes that C terminus makes an additional entry into the membrane itself, giving us 4 loops. So you'll see a little bit of variability in terms of the inside or cytoplasmic loops, in terms of whether you see 1, 2, 3, or 4 of those loops. Typically, intracellular loops 3 and 4 are the places where there's most significant interaction between the receptor and the G protein itself. And so the transducing of the signal that's coming into the cell from the outside to the inside typically occurs with respect to important residues, amino acid residues that are found in loops 3 and 4, although loops 1 and sometimes 4 also contribute to that linking of the receptor itself to the G protein. So that surface that exists between the binding determinants of the receptor and the G protein itself is an extraordinarily important area because of that ability to move that signal from the outside to the inside via loops 2 and 3. So a lot of work has been done from one type of G protein coupled receptor to another with respect to which particular segments of loops 3 and 4 are involved in transducing that signal. And as you can imagine, those segments of intracellular loops 2 and 3, which are coupling to the G protein, are potentially of great interest as far as regulation of the receptors are concerned, and indeed even potential development of new drug substances, which are mimicking the regions of loops 2 and 3 with the receptor, because those are control points with respect to the receptor. So there's maybe a lot more to this particular cartoon than one might imagine, and try to talk about a few of those things here in the last few minutes. So as we go along throughout the semester and into next semester too, be referring back to this cartoon because it's kind of informationally rich and a nice way to think about things as we're looking at discrete examples of G protein coupled receptors, of which more of those were listed in this next slide entitled endogenous ligands. And we talked a bit about this yesterday. So the endogenous ligands and the endogenous receptors, of course, are very much coupled to each other. And many of those endogenous ligands are drug substances themselves. And indeed, as we launch into autonomics here, probably later on this hour, acetylcholine is not only important as far as a physiological ligand is concerned, but it's actually a very rapidly acting and short-lived drug substance itself. And indeed, both norepinephrine and epinephrine over on the sympathetic side are not only physiological ligands, but drug substances. And then, of course, we'll see many other drug substances which are based upon the structures of acetylcholine, epinephrine, and norepinephrine, but with slight changes that influence their pharmacokinetics as well as their pharmacodynamics. So from a history of pharmacology standpoint, acetylcholine, norepinephrine, and epinephrine have been known for a long period of time, and their study realms date back to more than 100 years. Some of the substances listed at the bottom of the slide, such as the endorphins, of course, have been around physiologically for forever, but in terms of study as pharmacological aspects, their history is measured only in a few decades, as opposed to a century plus for some of the better known substances. So we talked a little bit about how the revolution in molecular cloning, which occurred a little after mid last century, led to not only an explosion of understanding in the physiological realm, but also in the pharmacological arena. And so the huge number of receptors, G protein coupled receptors and otherwise, which we know of now, has basically unfolded in about the last 3 to 4 to 5 decades at most. We talked a little bit about the structural aspects of the G protein coupled receptors. They're trimeric, but that structure goes a little bit beyond that, in that there's linkage between the alpha and beta subunits that's important in terms of the functional aspects of G protein coupled receptors, as well as, of course, the gamma subunit itself. And so we talked a little bit about how the alpha subunits are, one of the most active domains of the G proteins themselves, and you can see that in the homology numbers, which are listed here, which we talked about a little bit yesterday, in terms of, although there's quite a bit of homology from one type of G protein to another, there's not as great of homology there as there is with respect to the transmembrane segments of the receptors themselves, because of the tremendous utility of the theme of organizing those 7 transmembrane segments into functional aspects for the receptors. And so the binding determinants with respect to ligand and receptor itself are fundamentally owed to the transmembrane segments, whereas moving that signal into the cell itself is related to the G proteins, and particularly the G protein alpha subunits. And we talked a little bit about how there are subfamilies of these alpha subunits, the GS, which is a stimulatory subfamily oriented towards cyclic AMP itself, or the GIs, which are inhibitory towards the generation of cyclic AMP, are 2 of the most familiar subregions of the G protein, of the G proteins themselves. And then a somewhat a different subfamily in the GQ family, which are very much oriented towards membrane lipids, as opposed to the adenylate cyclase coupling of the cyclic AMP oriented GS and GI families. So there's a huge segment of neurochemical science which is devoted to study of the G proteins themselves, and we'll be looking at some aspects of that. Certainly not all of it, because we could devote the rest of the year to looking at the neurochemistry of the G proteins themselves. But for our purposes, the G proteins are very important in a functional sense in terms of how that relates to the perturbation of these receptors via drug ligands. So let's move ourselves away from the G protein coupled receptors for just a little while. We'll get back to them in due order as we move into the autonomic nervous system, for sure, because many of the autonomic receptors are G protein coupled receptors. But on the other hand, many of the autonomic receptors are also ion channels. And in the next slide, we'll see some hopefully useful cartoons for people to think about with respect to the at least some of the ion channel receptors. And they're of course transmembrane receptors in their own right. In fact, they're more complicated transmembrane receptors than even the G protein coupled receptors are. And you'll see some relevance of these cartoons with respect to our interest in pharmacology, because as I think you can see on sort of center screen there, but a little bit on the lower and the right hand side, you'll see, if you count those transmembrane segments, there are 5 themes of alpha, beta, gamma, and delta, with alpha repeated with respect to the this class of ion channels. But even within the realm of the alpha, beta, gamma, and delta transmembrane segments are further details as far as transmembrane neurochemistry is concerned. So the ion channel receptors are extraordinarily complicated and diverse, and there are plenty of examples of those diverse receptors that exist within the first realm that we'll tackle of the autonomic receptors here just shortly later this hour. So some important receptors as far as our look at pharmacology is concerned are represented by ion channel receptors such as for sodium, potassium, chloride, and calcium. And you see that cartooned in this next slide. A little bit more detail with respect to the next slide, which is entitled Sodium Voltage Gated Channels. And these receptors are incredibly important. A little bit later on this semester, when we talk about, first of all, local anesthetics, and then later general anesthetics, as well as next semester when we talk about the heart in great detail, and how these receptors are critical as far as maintaining rhythm of the heart is concerned, or in cases where things go bad, creating arrhythmias, which then have to be corrected by a variety of techniques, some of which are drug related. At the lower sort of right hand aspect of this slide, you'll see targets for natural toxins such as tetrodotoxin and saxitoxin. So that's an important topic as far as toxicology is concerned, but also with respect to pharmacology. And there are some mimicking of drug substances with respect to naturally occurring toxins, and so those will be discussed as in both physiological and pharmacological realms. Tetrodotoxin itself is an extraordinarily interesting subject, even sort of beyond the pharmacological and to the toxicological. Tetrodotoxin comes physiologically from an organism known as the puffer fish, which is an extraordinary delicacy, really, as far as the nutritional realm is concerned, but you have to be awful careful about how you prepare the puffer fish for its use as a food substance, to make sure the aspects of it that are involved with tetrodotoxin are not included in that nutritional dish that's being prepared at that time. So we cross over a little bit into the nutritional realm, as well as the pharmacological, toxicological, and physiological realm when we're talking about the puffer fish. So there are also ligand-gated ion channels, which are extraordinarily important in our look at pharmacology. And one of the really critical realms there, which you'll hear a lot about again later on in this semester, comes from the glutamate receptors. And the glutamate receptors are so important because there are representations both in terms of G protein coupled receptors as well as ion channel receptors with respect to glutamate. And glutamate is a neurotransmitter substance which has taken on star-like qualities here in the last few decades. When I was in graduate school, the glutamate receptors were not known at that time. It's really only in the meantime that they have taken on such a role in physiology and pharmacology. And one of the reasons for that was that, as you know, glutamate is an amino acid which is also involved in the formation of polypeptides and peptidal and protein substances, found in extremely high concentrations. And those high concentrations in the role in the realm of proteins kind of hid glutamate's role as a neurotransmitter substance. And it took quite a long time to establish the criteria for glutamate as a neurotransmitter, as well as its role in the formation of peptides. But that's occurred now. And so a very fertile area of investigation is in the realm of glutamate. And indeed, in our very own department, there's a lot of study that goes on with respect to glutamate as a neurotransmitter substance and its interactions both with ionophore versions and G protein coupled versions. So the nicotinic acetylcholine receptor is one of the most heavily studied of the ion channel receptors. And I kind of like this little cartoon here. You can see the subunit relationships a little bit better than you can in some of the other cartoons that we've looked at. So in terms of the history of autonomic pharmacology, for example, the nicotinic acetylcholine receptors actually have a longer history than the G protein examples in the realm of acetylcholine. The G protein coupled examples being the muscarinic receptors. So as we launch into autonomic pharmacology here later on in this hour or this afternoon, we'll see representations on both the nicotinic and muscarinic side, and in both central and peripheral pharmacology. a really interesting toxicological substance, alpha bungarotoxin, is in an area that's been studied for many decades. And we'll make referral to that as we go along, because the things that were learned about bungarotoxin are certainly relevant beyond the realm of toxicology. So we talked about the idea that there are other types of receptors beyond the realm of G protein coupled receptors, beyond the realm of the ion channel receptors. And sort of the best known example of that are in terms of the receptor tyrosine kinases, of which the insulin receptors themselves, if you look down in that next line on the receptor, are the prototypical examples. So a really great exam question that you just finished correctly would be, what are the prototype receptor tyrosine kinase receptors? And the examples there would be the insulin receptors. Of course, there are many other types of ligands which interact with receptor tyrosine kinases, and you see some good examples of hormonal growth-like factors listed in that next line, such as epidermal growth factor or platelet-derived growth factor or neurotropic-derived G protein, tyrosine kinase receptors. So these are diverse classes of molecules themselves, but not quite as diverse as the G protein coupled receptors or I'm having some senior moments here, or the ion channel receptors. But nevertheless, there are still many receptor tyrosine kinases. And they are very much involved in a variety of physiological actions, including cellular growth and differentiation, and therefore are extraordinarily important as far as drug action is concerned, as well as in the physiological realm. And typically, these transmembrane related factor receptors are not quite as intricate in their transmembrane segments as either ion channel receptors or G protein coupled receptors are. There's typically two transmembrane segments. And the two segments basically come from the fact that these receptors often act as dimers. And so you'll have extracellular regions, a transmembrane region, and then an intracellular segment of the receptors. The joining of a single monomeric receptors into dimers, you can see represented as you move from left to right across this particular slide. These are truly receptors which are cell surface receptors. They don't have a sort of a buried binding pocket like we see with the G protein coupled receptors. So these truly are interacting only with substances which are interacting with the external surface of the cells. And so the extracellular segments of these receptors really are businesslike in terms of interacting with ligands, be those physiological ligands like insulin, or drug substances, of which, of course, insulin is an example there also. That signal is transmitted across the membranous region by the transmembrane segments, and then get to the intracellular segment of the receptors, which is where the kinase activity comes about. And so phosphorylation events of the intracellular receptors with intracellular components is where that informational content of the drug or physiological receptor gets inside the cell. One thing that's notable about the intracellular kinase segments of these receptors is that the kinase segment is built right into the receptor. Now that differentiates these receptors from cytokine receptors, which do not have onboard phosphorylation segments, but in the kinase receptors, such as growth hormone receptor, there's another exam question that you just got. What is the prototypical cytokine receptor would be for growth hormone? You'll see the extracellular segments, you'll see the transmembrane segments, but you won't see an intracellular segment for the cytokine receptors, which upon agonist activation of the cytokine receptors is recruited from the cytoplasm. So just a little bit of difference thematically there between the cytokine receptors such as growth hormone, which do not have an onboard kinase segment, and compared to the insulin receptor tyrosine kinase receptors, which do. So you might think about that just a little bit in terms of differentiating these two subclasses of kinase receptors. So here's just a little bit more detail with respect to the receptor tyrosine kinases themselves. And so if you were to blank out the lower parts of this cartoon with respect to the cytokine receptors, you would see the absence of these endogenous kinase regions with respect to the cytokine receptors themselves. So you sort of see that recruitment process going on here in the next slide entitled Receptors with Enzymes as Intracellular Effectors. And you can see the extracellular, the transmembrane segments, but not the onboard kinase segment until it's recruited with respect to these cytokine receptors. The theme of the intracellular segments is represented by some of the words here, and you see the JAK-STAT receptors, which are some of the most commonly recruited intracellular effectors as far as the cytokine receptors are concerned. And sometimes those JAK-STAT receptors are referred to as the Janus receptors, as opposed to the JAK-STAT abbreviation. So just a little bit of terminology going on in this particular case. The nuclear hormone receptors is another large family of receptors, and very different receptors from any of the transmembrane receptors that we've just been referring to, because these receptors are cytoplasmic in terms of the portion of the receptor that binds to the incoming physiological or pharmacological ligand. So they are not represented by transmembrane segments. The genesis of this group of receptors actually predates the G protein coupled receptors in terms of historical study by physiologists and pharmacologists. And so you can see historical representations of these receptors going back even into the 1960s, a little bit in front of the G protein coupled receptor realm, which didn't really unfold until really about the 1970s. So the original thought on the nuclear hormone receptors was that all ligand binding occurred with respect to ligand receptor interactions in the cytoplasm. That's now been expanded a little bit because some of the subtypes of receptors in this category actually have the first interaction between ligand and receptor occurring in the nucleus itself. So you see differentiation of these receptors in terms of whether the binding occurs in the cytoplasm or in the nucleus. But regardless of where that occurs, the drug receptor or physiological ligand receptor complex finds its eventual effector target in the nucleus, and therefore the name of the nuclear hormone receptors. And so these receptors are essentially transcriptional regulators, and that drug receptor complex is involved in regulating very discrete nuclear elements. And it takes a little while for all of this to unfold, as you can imagine. So one thing that's different about the nuclear receptors compared to the transmembrane bound receptors is that the nuclear receptors are kind of sluggish. They're slower. And so we tend to see time effects which are in the minutes to hours to longer in this realm, as opposed to the almost instantaneous types of effects that you see with respect to the transmembrane receptors. And so you can see some in this slide entitled Nuclear Hormone Receptor Function. They often act as dimers too, kind of like we saw with respect to the insulin receptors. But the difference here being the binding to specific DNA response elements. And so little bit of the cartooning you want to pay attention to with respect to these receptors. So classical nuclear hormone receptors are the steroid receptors. And so the estrogens, the progestins, the androgens, and so on, find very much of their action associated with the nuclear hormone receptors. But as we'll see, there are some complications that exist with respect to that as we get into hormonal function later on in the year, in next March and April specifically. So there's all these different things going on with respect to signal transduction, and the integration of these responses with various types of receptors that we've been talking about here occurs in that complex intracellular environment. And the real revolutionary aspects of the future of these receptor functions is very much in the realm of signal transduction, as they're integrating the signals that are coming from these diverse types of receptors to the intracellular compartments themselves. And so when we talk about what's going on inside the cell in terms of what makes a drug what it is, we're very much talking about signal transduction at that particular point. And it's an informationally driven sort of process that's going on as we're taking extracellular information and transmitting that to the inside of the cell by one mechanism or another. We've just seen some different approaches taken to that with these various receptor subclasses in the last few minutes. And so as we think about drug action, ultimately it's what's that moving that information to the inside of the cell, which is producing the drug effects which are of great interest to us. So we'll conclude our look at pharmacodynamics in a general sense now and move to the discrete realm of autonomic pharmacology and how that relates to autonomic physiology as we open up our discussion this afternoon at 1 o'clock. So I'll take any questions that people might have at this point, and when we're done with that, take an hour break and see you again at 1 o'clock with Introduction to Autonomics. Well, enjoy activation of your parasympathetic nervous systems, everybody, because the parasympathetic nervous system is involved in moving nutrients into the system and storing those nutrients. And that's about what you're going to do soon now with lunchtime, hopefully. So see you in an hour, everybody. Take care.